So let us utilize the ideas that we have learned in the Reynolds transport theorem to do conservation of mass. Okay, so the Reynolds transport theorem said that if we have a control volume moving with the velocity b, then the rate of change of any quantity f contained in the control volume is equal to the following. Okay, so we appreciate the fact that ddt is also ddt because it's a Lagrangian term and it's essentially a total derivative. Okay, so we are tracking this mass as it goes through the fluid. We are tracking as it travels with velocity b. Okay, now b may or may not be equal to the fluid velocity u. Okay, there is no necessity of b may not be equal to u. U is the fluid velocity. Okay, so now if we set f equal to rho, then the statement reduces statement above, it becomes mass conservation. If f equal to rho into u, then the above statement boils down to momentum conservation. And so on. So set f equal to rho in the above. So we have d dt of integral rho dv. This is equal to integral of del t rho dv plus integral rho b dot n dA. So the rate of change of, so this implies this particular term, this implies rate of change of mass held in the volume moving with velocity b. Okay, this term implies temporal change in density, and this term arises because of a flux of mass across the deforming boundaries. Okay, so proceeding, if we choose b equal to u, then essentially we are tracking a volume in the fluid. We're tracking a deforming volume through a fluid. Deforming volume moving with the fluid velocity rather. Okay. So essentially we are sort of tracking an identified volume as it moves and deforms. Okay, so the mass held inside a volume is always going to be constant. Mass inside identified volume moving with the fluid velocity is constant because there is no generation of mass or reduction of mass. Therefore, the ddt of integral rho dv, this term is equal to 0. This is equal to integral del rho del t dv plus integral rho, b is equal to v, so u dot n dA. Okay, so we have 0 equal to integral del rho del t dv plus integral rho u dot n dA, isn't this by v and a. So these are the integrals over the volume and integral over the area respectively. However, we are often concerned not to we are often interested in not to track the fluid with the fluid velocity. In this case, it is easier to generalize the RTT for mass conservation. RTT stands for the Reynolds transport theorem. So Reynolds transport theorem told us already that if we have a volume moving with some arbitrary mass, I will use the d instead of capital D, it's easier for me. So this was in general V star, V star. The star indicates the fact that the volume is not moving with the fluid velocity. Sorry for that. Okay, so the RTT in general tells me that ddt of rho dv is this. So we have thus two frames of reference, one moving with a velocity b and one moving with the velocity u. In this frame, ddt of rho dv is identically 0, but for this frame it may or may not be 0. Okay. So at a time where the two volumes coincide, where the two frames coincide, V star and V coincide. They are moving with two different velocities, but at a time where they coincide, we see that the rate of change of time, it does not depend on the velocity. Okay, if I call this the term 1 and this is the term 2, the term 1 does not depend on velocity. Okay, it only depends on the local rate of change of rho. So it is independent of the frame. Thus, when the two frames coincide, integral V star del t of rho dv is equal to integral in both the frames. Okay. So if I call this equation as equation 1, this equation as equation 2, and this equation as equation 3, I can substitute the value of del rho del t at V equal to this. So I will substitute, okay, let's write down from equation 1. Integral V del rho del t dV is equal to minus integral rho u dot n cap dA. Okay. And so if we use this equation write this equation as 4. Use equation 4 in equation 2. We will substitute whatever is this, whatever is this from this. So we have ddt of rho dv is equal to minus integral rho u dot n cap dA plus integral rho b dot n cap dA. Okay, but this integral v star was the same as v, so at this instant it becomes equal to v. This we get rho b minus u vector dot n dA. Thus, the conservation of mass for a control volume moving with an arbitrary velocity b. So b need not be constant or uniform or anything, but it need not move with the velocity of the fluid. So integral rho u minus b dot n dA is equal to 0. Okay, so this is the integral statement of the conservation of mass. And we'll do some problems related to this. Okay.